Hello everyone, this is CSM16A discussion 3 question 2, and we're going to walk through this question called I guess you can be there or be square. But fundamentally in this question we're going to try to do an eigenvalue proof so that you can learn more about what you currently know in lecture as conservative state transition systems. So let's just start off with one subpart of the question, which is a helpful property it proclaims itself. We're going to try to prove for the prompt that the square matrix A and its transpose A transpose should have the same eigenvalues. And our hint here is that for any square matrix, determinant of B is equal to determinant of B transpose. Now, the relationship between determinant and eigenvalue is associated to the definition of an eigenvalue. By definition, lambda is an eigenvalue of A if the determinant of A minus lambda I is equal to 0. In other words, if I have an eigenvalue lambda for this matrix A I mentioned in the prompt, then that means that the determinant of A minus lambda I is indeed equal to 0, and via our hint, we also know that the determinant of A minus lambda I transpose should also be 0. Now here's an interesting thing, which is that I, the identity matrix, is a diagonal matrix. So the diagonal matrix and its own transpose are in fact equal to each other because the identity matrix itself is symmetric. This means that we can then derive the determinant of the transpose of A minus lambda I into determinant of A transpose minus lambda I. So therefore, by definition, we see that since the determinant of A transpose minus lambda I is 0, lambda is also an eigenvalue of A transpose. We can prove this in the opposite direction. If the determinant of A transpose minus lambda I is equal to 0, then that means the determinant of this entire thing transposed, which I'm going to write out here instead of speak it because it's very complicated to say, can then be derived by the algebraic work I'm going to present to you as just A minus lambda I. So if we know that the determinant of A minus lambda I is equal to 0, then lambda is an eigenvalue of A. So via this kind of bidirectional proof where you prove that if an eigenvalue, if lambda is an eigenvalue of A, it must be an eigenvalue of A transpose, and if there's another value, say another lambda that is equal to the eigenvalue of A transpose, it must also be an eigenvalue of A, we can then see that the square matrix A and its transpose must all have the same eigenvalue. Now another property you can relate to for this proof is trying to prove that underlyingly the set of lambda or the set of eigenvalues of A is equal to the set of eigenvalues in A transpose. Which would probably remind you of some kind of vector space proof that you will have to do during Eiguess16A. And the concepts we have used above use a very similar logic to prove that the set of eigenvalues of A is indeed the set of eigenvalues of A transpose, by proving that each member of one set belongs to the other set, and therefore proving that the set of eigenvalues are equal. We know that the set of eigenvalues of A is equal to the set of eigenvalues of A transpose. Now that we have solved part A, let's move on to another perhaps helpful subproof, which is part B, to prove that for a square matrix A whose rows sum to 1, the vector 1 is one of its eigenvectors. Now the vector 1 here is a shorthand notation for a column vector whose entries are all 1. So if we directly so let's first remember that if one vector is indeed one eigenvector, then there must exist a lambda such that A times the vector 1 is equal to lambda times the vector 1, and that is because this is the definition of eigenvalue and eigenvectors. Here, once again, the eigenvalue is lambda, but you probably already know that. And I will just restate this fact here. Now, our task then is to find such a value lambda, because if we can prove that such a value lambda exists, then lambda and the vector 1 is indeed one eigenpair of matrix A. So let's try to compute A times vector 1 and see what happens. For what I'm going to do, I'm going to write A in terms of its components, because that might help us later. So I'll go all the way from A11 to A1n, and I'll write down the rest of the components on the screen so that you can see them. Also, another very important fact that we should continue to remember from the prompt is that the rows of A sum to 1. So, multiplying the matrix A with the vector 1 is itself equal to the vector whose entries would then be the row sum of matrix A. Let's go through the inner mechanics of this. So the first entry of our resulting vector is going to be A11 times 1 plus A12 times 1 plus A13 times 1 plus da 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 plus A1n plus times 1. And this happens to be the sum of the first row's components, which in turn means that this is going to be the sum of the row of matrix A, and that is going to be 1.
Who's trashed? Oh.
Alright, so now that we know that the resulting vector of multiplying matrix A and vector 1 is the vector 1 itself, we see that the equation above can be rewritten as A times vector 1 is equal to vector 1. The eigenvalue here then is then equal to 1. So we see that the lambda equals 1, the eigenvalue 1, and the vector 1, which is very confusing in terms of verbal, so you have to look at the notation here. But you'll see that the eigenvalue 1 and the vector 1 forms an eigenpair for the matrix A. And thus we have proven that the vector 1 is an eigenvector because we have found a corresponding eigenvalue for it. So now let's move on to part C. Part C combines the knowledge from part A and part B, but we'll go through that part later. So, prove that if a matrix A resembles a conservative state transition matrix, one of its eigenvalues is lambda equals 1. How can I know this? Well, first of all, let's try to translate the prompt a little to get some information. I'm going to write a couple of bullet points under this section called what we know. First of all, A is a conservative state transition matrix. Which I'm going to write in shorthand as ST matrix. This means that its columns sum to 1. Also, we know that we're trying to prove its eigenvalue is lambda equals 1. And let's also consider what we have proven in the previous part as what we know. So one of the knowledge that we have proven is that A has the same eigenvalues as A transpose. And we also know that if the row sums of A is 1, or are all 1, which is a better mathematical explanation, then it has the eigenpair of eigenvalue being 1 and the eigenvector being the 1 vector. We know all of these. Well, first of all, let's consider that A has the same eigenvalues as A transpose. So if we find the eigenvalues of A transpose, we can find the eigenvalue of A, which is the matrix of prompt. And second of all, let's also consider what A transpose, what feature A transpose has, given that all columns of A sum to 1. This leads us to the fact that all rows in A transpose sum to 1. Let's look at this a little more closely. A itself expressed in components is going from A11 to AN1, going to ANN, and the AN1 here. Now let me write down A transpose in its components. This should be A1N here. And then here we go. You will see that if I express A as a matrix of its columns A1 to AN, which correspond to the columns above that we have in matrix A, then the matrix A transpose would be equal to a matrix resulted by stacking the transposed version of the column vector, and you can see that from the component expression here. I'll leave the screen here for 5 seconds, and if you want to pause the video and try to see this relationship, please feel free. Alright, so that's around 5 seconds. That should be enough time to pause the video. Now I'm going to go on and continue discussing why the rows of A transpose should sum to 1. So you see that each column in A, according to its property of being a conservative state transition matrix, should sum to 1. So we know that all of the column vectors here from A1 to AN have their components sum to 1. Now we see that A1 transpose is the first row of A transpose, and in general the vector AI transpose is the ith row of A transpose, which means that each row sum in A transpose is equal to the column sums in A. So in other words, A1 transpose sum up to 1, meaning that the first row of A transpose sums to 1, and AN transpose sums to 1, meaning that A transpose row at A transpose's nth row sums to 1 as well. If A transpose rows sum to 1, then according to what we have proven in part B, it must have the eigenpair lambda equals 1 and vector v equals 1. So the fact that A transpose rows sum to 1 leads to another fact that 1, 1 vector is an eigenpair of A transpose. So written in literal mathematical terms, A transpose times 1 vector is equal to the 1 times 1 vector itself. So we know that 1 is an eigenvalue of A transpose. We know that 1 is an eigenvalue of A transpose, therefore by what we have proven in part A, let me also write part B here so that it's clear what we're doing. We have proven in part A that if lambda is an eigenvalue of A transpose, it must be an eigenvalue of A as well. So 1 is also an eigenvalue of A. At this point, we have then proven the prompt. So what does this really mean mathematically? Well, you will talk about this afterwards when you talk about eigenanalysis, which is probably when this worksheet is published, so let me just talk about it. In eigenanalysis, you'll see that when you're trying to find the state-state vector of a state transition matrix, whether you'll have a zero steady state really depends on what your eigenvalue is. In this case, if your original state that you're trying to derive a steady state for has some kind of linear combination involving the eigenvector of eigenvalue being 1, then what happens is that that eigenvector persists until the steady state, and therefore we will not have a zero steady state. For example, let's say that A itself is once again a state transition system matrix, and we're going to have another state, A, X. let's say that A has n eigenvalues such that x itself is equal to lambda 1 v1 plus plus. Actually, let's change the term here. Let's say that x is equal to a linear combination of A's eigenvectors, which once again there are n eigenvectors. So x is equal to, say, alpha 1 v1 plus plus alpha n vn. And let's say that one of the eigenvalue is 1. So I'm going to say 1 here. Then what happens is that when we're trying to find the steady state, which is when we multiply x by a infinite times, then we're going to get the following expression, where we're going to see that this expression is equal to 1 times lambda 1 to the nth power v1 plus alpha 2 times lambda 2 to the nth power v2 plus plus alpha n times lambda n to the nth power vn. Let me change this n into infinity so that it's easier for everyone to see what's going on. And let me change the terms here, so it's easier to see what's happening in this expression. Alright, so now we're given this information. We see that lambda 1 itself is equal to 1, so equivalently I am just multiplying v1 by 1 to the infinity power, which would just then be v1. So then this entire expression, or in other words, the steady state of the state transition matrix given the initial state is x, will then be equal to v1 plus, and then I'm going to sum over alpha I, lambda I to the infinity power, and their corresponding eigenvectors, which some of these terms might end up being 0. So if we have an eigenvalue of 1 and we have a corresponding eigenvector as a component of the initial state, then we'll see that the steady state will at least not be equal to the 0 vector because we still have a vector v1 in here. Well, what if v1 is 0? Unfortunately, eigenvectors cannot be the 0 vector. So we have a guarantee by definition that v1 is not equal to 0. There might be another case where your initial state doesn't involve the eigenvector v1 as well. Then in that case, yes, since the coefficient of v1 would then just be 0, then you will not see v1 in the steady state. Thus, you are not really guaranteed to get a non-zero steady state transition as well. Let me expound that a little bit more. Say that I now change the coefficient of v1 to alpha 1, which is an unknown scalar. So the steady state I'm left with would at least be alpha 1 v1. So your steady state would be non-zero if alpha 1 is not equal to 0. Okay, hopefully that was a good summary of the implications of what we have proven in part C. So now let's move on to part D, where we will then prove that for a square matrix A whose row sums to n, 1 is one of its eigenvectors. And then we'll try to find the eigenvalue of this corresponding eigenpair. But in fact, our proof that 1 is an eigenvector already involves the process of trying to find an eigenvalue corresponding to the vector 1. So in other words, we're just doing part B, but this time all of the rows sum to n. In that case, let's really quickly review what we have done in part B. In part B, we try to formulate an equation A vector 1 is equal to lambda vector 1, and by finding lambda, we prove that lambda comma 1 vector is an eigenpair of matrix A therefore vector 1 is an eigenvector of A. So now let's try to find lambda. Once again, I'm going to write out everything in component form, so it's easier for people to see what's going on. Alright, let's write the column vector 1, 1, 1 here. Okay, so once again, this is going to be equal to a column vector whose entries will be the row sum of matrices, the row sum of matrix A. Let's go through the reasoning one more time, just in case people have forgotten about this. So the first entry of the resulting vector in the product is, once again, a11 times 1 plus da-da-da-da-da times 1 plus a1n times 1. The last entry of the resulting vector is equal to an1 times 1 plus an2 times 1 plus da-da-da plus ann times 1. So, in other words, the entries we get along the solution column vector we have on the right-hand side of the equation are just row sums of the matrix A. And as the prompt has spoken, they should be equal to n. Which this vector itself is then equal to n times the 1 vector itself. So that's pretty convenient because this means that A times vector 1 is equal to n times vector 1. Therefore, the eigenvalue corresponding to the vector 1 is n itself. Now let's talk about part E, which is recorded on a different clip for reasons that I should not tell. So part E asks us this tricky part of the question where suddenly my friend who studies Eiguess16B challenges me to a proof battle. The prompt is that prove for every square matrix A whose rows sum to 0, so sum to n, not columns, it must have an eigenvalue of lambda equals n. Note that this itself is equivalent to the prompt that prove A transpose has an eigenvalue of lambda equals n as well. We'll see that it might come in play. We'll see that it may come in a very convenient format later when we're trying to deal around the hint of the proof, which is that for any square matrix A, if I add rows together inside A, then it must be that the determinant of A is equal to the determinant of A after I do the row operation. Mind that the row operation we mean here is adding row operation, which means adding and subtracting rows that just as you have been doing in Gaussian elimination. So no, you cannot multiply rows by scalar. That's going to cause very interesting properties that are going to make the determinants unequal. Well, first of all, what's the relationship between determinants and eigenvalues again? Right, it's that if determinant of A minus lambda I is equal to 0, then lambda is an eigenvalue of A. In other words, the equivalent prompt that we're trying to prove is that prove the determinant of A minus Ni, which is equal to the determinant of A transpose Ni, is equal to 0. So with that being noted, what I'm going to do next is to try to prove this claim. First of all, it will be very convenient to see what A minus Ni and A transpose minus Ni looks like. So for now, I'll deal with A transpose minus Ni because that's what we're going to deal with next. I'll talk about the reason later. And we have a Ni, which is just the identity matrix multiplied by n, so we'll see n's along the diagonal and 0 everywhere else off the diagonal. So this matrix itself is inherently equal to, well actually I should fix the components here because they're not making sense since they're in the transpose. So once again, the components of the matrix will end up being, first of all, the diagonal terms are all going to be subtracted by n, but everywhere else is not going to be affected by subtracting Ni because every non-diagonal term of the matrix Ni is equal to 0. So we'll end up having a matrix that looks something like this. And mind that since this is subtracting Ni from the transpose, the components will seem slightly different than what people might have expected, which is that we're going to reverse the indices of each term. So once again, the component should look something like this. Oops, let me write out this matrix bracket a little more clearly. Okay, so mind that adding row operation doesn't affect determinant. And also mind the fact that we need to prove determinant of A transpose minus ni is equal to 0, such that we can prove n is an eigenvalue of A. So what we will then need to do is try to find some kind of way to say that determinant of A transpose ni is equal to 0. Well, very fortunately, adding rows together doesn't affect the determinant, so what if I just add all the rows together and see what would happen? Well, if I add all the rows together, then I'll end up with a row vector, which is basically, the first entry is going to be a11 plus plus a1n minus n. The second entry is going to be a21 plus plus a2n minus n, until the last entry of this row vector, that is the sum of all rows, is equal to an1 plus plus ann minus n. All of these entries actually sum up to 0, because we know that the row sum of A is 0. The row sum of A is n, according to the prompt. So this component is 0, which means by adding all of the rows in this vector in this matrix together, we end up having a row of zeros. So if I perform a row operation where R1 is equal to, R1 now becomes R1 plus plus Rn, then I will end up with a matrix that looks like this, where it has a row of 0, and it has the rest of the rows being normal. Let me write this out very clearly so that it is viewable. This is a22 minus n, and we go from a32 to a n comma 2, and we have a lot of terms in between that can be expressed in diagonals, and the last term here is n comma n minus 1. And mind that since the first row is equal to 0, the determinant of this entire matrix would then have to be 0. Therefore, n is an eigenvalue of A transpose where all of the columns sum to n. And therefore, n must also be an eigenvalue of A, according to what we have proven in part A. And that is because all rows of A sum to n. And, well, not because, it's that it is a fact that all of the rows in A sum to n, and n is an eigenvalue of A because n is an eigenvalue of A transpose. And surprisingly, we have now proven the prompt.